Okay, students, welcome. I decided I'd start that one off with a guitar introduction for something for a little different. All right, that's a song by the great Tommy Emmanuel. It's cut short by about 5 minutes, but a beautiful song called Endless Road. Okay, so to get going on this, what we're going to do is look at functions, first derivative, graphs, kind of talk about how we can use calculus to find lots of things about a function, like whether it's increasing and decreasing, max and min, and things like that. Okay, so to begin with, what we're going to look at is a function is increasing when the first derivative is positive, and we'll talk about that a little bit. So that just means that you find an interval on the graph where the slope of the tangent lines are positive, then the function's increasing. A function is decreasing when the first derivative is negative, and we're going to begin to look at that a little bit. Okay, so I got this thing's kind of funny. I found this thing on the internet, and some of the things people come up with sometimes are kind of funny, but I thought it was worth showing. The first thing I want to do is remind you of what we mean by a function increasing and decreasing, just to begin with. So this one's kind of funny with the turtle on it. So the idea is a function would be increasing when the y values get bigger. So you can see the turtle is going uphill. This function is increasing right now, and the tangent line is positive during that time period. Now I'm going to stop here. Now the turtle is up at what we call a local maximum. The derivative is 0. The slope of that tangent line is 0. Now the function's going to start decreasing. That's not what I meant it to do. So anyway, we got the turtle going uphill. We have a positive tangent line. Okay, now the turtle's going to go through the decreasing part of the curve. So he's going down the roller coaster. Now he hits the low. We call that a local minimum. And then change directions, the slope of the tangent line becomes positive. So the turtle is going up the roller coaster. It's beginning to increase again. Okay. What I want to show you on this, and one thing that's actually kind of cool about this is if you were to graph the first derivative, what would happen is this would be the graph of the first derivative. If you took the derivative of this function and graphed it, you would have this. And what that's saying is all of these values here are positive. Okay, on this part where the function was increasing, the derivative has positive values. In this place where the function was decreasing, which is this red region from there to there, the graph of the derivative would have negative values, okay? And then in this green part where it's increasing again, the derivative would be back to having positive values. So basically the derivative is positive, then 0, then negative, then 0, then positive. Okay, so I thought that was kind of cool. Right. One other thing that I found on the internet that shows this pretty well is this actually I think shows this real well is this is a function. This is just the graph of x squared. And then this represents the tangent line on here. So I want to show you what's happening. Just watch these y values. So when the function is decreasing, you're going to see these y values getting smaller. Okay, so right now the y value is 20, 19. So the y values are getting smaller. Eventually you get to this point right here. It's kind of hard to stop on here where the function value becomes 0. So through that region, you were always, the y values were getting smaller. Now we're going to increase, watch the y values get bigger. So if you just kind of watch that y value as I go through this, you're going to see those y values are getting bigger and bigger and bigger. Okay, so like I was showing on the turtle thing, okay, what's really happening on this is the slope of the tangent line, and this thing is actually doing the slope of the tangent line. Right now it's negative, so I want you to watch as I manipulate this tangent line. Watch how that tangent line slope is still negative. So it's negative, still negative, still negative. Eventually you get to the point where the slope of the tangent line is now 0. Okay, now what happens is the slope of the tangent line turns around and becomes positive, and it actually gets bigger. So the slope of that tangent line is getting steeper and steeper like that. All right, so those two things should hopefully show you pretty well what I'm talking about by that basic fundamental definition. Okay, so what we typically do a lot of times in this section is we take functions, and what we do is we work with a derivative, and we end up making a sign chart to analyze the value of the derivative. So without going through the details on this function has a derivative of 3x to the third minus 3. If I was to go through and factor this, I could pull out a 3. Then I could factor this as a difference of 2 squares. So you'd end up getting this factoring. And what you would end up getting is x plus 1 is 0, x minus 1 is 0. So you would end up getting 2 places where the derivative of this function would be 0. Okay, so those would be what we're going to call critical points. And critical numbers are places where the derivative is 0 or where it's undefined. Now what would happen, and we'll get to this as we learn this section, so if you took this function, this is the graph of f of x equals x to the third minus 3x. If you did a sign chart, so if you looked at x equals -1, the derivative would be 0 right there at -1. The derivative would be 0 here at 1. And then you would find that the derivative would be positive in here, negative in here, because the slope is, the tangent line's negative, and then positive here. That's what I was showing you with those two applets. So what you're going to learn how to do, and we'll do a ton of this in this section, is take a function, make what we call a sign chart to make determinations. So what you would find in this case is the function would increase because the derivative is positive, decrease because the derivative is negative, and then increase because the derivative becomes positive again. So that's the idea that we're going to be establishing with the calculus. Okay, this is just showing something we've learned before. This would be an example of the function increasing. Then constant means that the function's not changing. Okay, it's like flat, then it's increasing again, and then it would be decreasing. You always read from left to right when you do that then. Okay, so in a nutshell, those are the basic things that are going to define a lot of what we do in this section. You want to know that when the derivative is positive, the function increases. When the function's negative, it decreases. You're going to learn how to do sign charts. And then a critical number is going to be where the derivative is 0 or undefined. Okay, a critical point is a point that's on the graph. Okay. All right, next page we'll kind of get to work, and the first thing we're going to do is just take graphs and identify intervals. We've already done this in this class, so what we're going to look at on this is what a local extrema is. A local extrema, and you might write this down if you want to, basically what we call a local min. What's going to happen is the graph is going to decrease, then it's going to increase. Okay, so in other words, you're going to find a place where the function decreases, then increases, and we call that point a local min. A local max is going to be a place on the graph where to the left of that point, the function increases, then it changes directions and starts decreasing. So you would have a place where the function might look something like that. It's going to increase, hit a high point, then decrease. Okay? So we're going to find all of the local minimums on this point. And you got to be careful on this. The local minimums would be at this point because the function decreases and then increases. So one of the points that would be a local minimum would be at x equals c2. Okay, another place would be right here. The function would decrease, then increase. So we would also have c4. Okay, and actually that's it. This is not a minimum because the function decreases, but on the right side of that point it also decreases. So that is not a definition of what a local min is. Okay, now let's look at the local maximums. Okay, the local maximums would occur at a place like this where the function increases, then decreases. So that would occur at C3. Another local maximum would occur here. The function increases, decreases, and that would be actually it on that. Okay, these points here, right here, so let me just kind of show you the maximums are the yellow points, and then the minimums would be this place and this place right there. Every other point on the graph does not satisfy the condition of it being a local max or local min. Now, if I was to find every place on this graph where the derivative is 0, that would mean where is the tangent line horizontal? That happens several places. That happens there, here, here. It doesn't happen there because the derivative does not exist. It happens here. It doesn't happen there because the derivative doesn't exist. Doesn't happen there because the derivative doesn't exist either. So the places where the derivative would be 0 would be C1, C2, C3. Not here, but it would be at C5, and that would be it. Those are the only places that I've marked on that graph where the tangent line is horizontal. Okay. Remember, if you have a sharp point, the derivative does not exist. Okay, it's not differentiable at that point. Okay, now if we look down at the next thing on here, we're going to look a little bit at looking at where a function increases and where it decreases. So first of all, I'm just going to kind of go through and let's start with where it decreases. And I'm going to highlight this. So the y values are getting smaller. You're going downhill until you get there. The next place it would decrease would be from here to there. And you're going to name these intervals open intervals. So you're going to use parentheses on this. So this would be from negative infinity to 1. That's where that would happen. Okay, then it would start up again from 3 and then to 4. That would be where that function is decreasing. Where that function is increasing is going to be from here to here. The y values are getting bigger. You're going up the roller coaster. And from there to infinity, you're going up the roller coaster. All right. So we would say from 1 to 3 in that open interval, and then from 4 and beyond. So that's how we would name them. Okay. Local minimum. How many local minimums do you think there are on this problem? Okay, there's one right there. That's a min. That establishes the graph is decreasing then increasing. Same thing here. That's a minimum. The graph changes directions from decreasing to increasing. So we're going to give the coordinates on this. The coordinates are 1, -1. These are not intervals. These are points. And then this point is 4 and maybe a half, or I don't know. It's hard to say. I'll say 0.6. What the heck? Okay, so I'm just estimating. All right, a local maximum would occur. I think this is supposed to be a maximum. How many local maximums do you see in the problem? Okay, yeah, there's only one. That would be the graph is going from increasing to decreasing. So that local max would be at the point 3,1. Okay? All right. Now, this is saying where is the derivative a positive value? Okay, so think about the tangent line. Where is the slope of the tangent line positive? That would actually be from here to here. In this blue region, the tangent lines would all be sloping upward. Okay, so they would kind of do something kind of like this. Okay, for instance, at that point right there, see that tangent line's got a positive slope to it. Okay, same thing in this region here. So we would say the derivative is positive from 1 to 3 and from 4 to infinity. Okay, now what I want you to understand on this is these are the same answer. A function is said to be increasing where the derivative is positive. Okay, next statement is saying where is the derivative, f prime of x, negative. Okay, so that would be examples of slope tangent lines sloping downward, kind of like this. So that happens, you know, everywhere in this yellow region here. Okay, I think I can slide this over and kind of make that. That would be an example of one place where the derivative is negative. So in these yellow regions, the derivatives are going to be negative. So that would occur from negative infinity to 1 and also from 3 to 4. Okay, and that would be the same answer as number 2, because a function decreases where the derivative is negative. Okay, so increasing and decreasing that's the connection I want you to make with the derivatives. Okay, one last thing we want to look at on here is where are the coordinates where the derivative is 0? So I want you to think about tangent lines that are horizontal. When the tangent line's horizontal, the derivative is 0. So how many places on this graph would the slope of the tangent line be 0? Okay, what'd you say? Okay, all right, that's good. So that would be here, here, and here. That would be at those minimums and maximums. Good. Okay, so we would say one place would be the point 1, -1. Another place would be the point 3, 1, where you have that maximum. And then the other place would be that point 4. And I think a minute ago we said that was about 0.6. Okay, so real important, you want to be able to look at a graph and visually tell intervals where it increases and decreases, visually determine points that are minimums or maximums, and visually determine where the derivative is 0. You get that going and do that effectively, then you'll understand all the main concepts primarily that we're going to learn in this section. Okay? All right. So let's see. What I'm going to do on this next page is do one more example of this, and then I'll put you to work on a few of these yourself. So this example 2, we're doing a different graph. First thing we're going to do is identify every place where this function increases. Okay? Well, one place would be from there to there. The function is the y values are getting bigger. You're going up the roller coaster. Another place would be from here to there. All right, and then a third place would be from there to there. So those would be all of the places where that function's increasing. So we would name this interval from the x values, -7 to -3. Then we would start again from -3 until we got to -1. Okay, then we would start again from 1 to 3. Now you may be asking, why did I break this up into 2 intervals? The reason I did this is because of that. You actually could have done this. You could have said -7 to -1, and I probably wouldn't fuss at you too much. But that is a sharp point, so the derivative does not exist there. So I went ahead and broke it up into 2 intervals. That really technically, it's kind of hard to tell that that's a sharp point, but it really is. That's going from a curve to a straight line. Okay. Next thing we're going to look at is where does the function decrease. Okay, that's going to be here to here and here to here. Now when you get here, this part right here, we would call that constant because the graph doesn't change. The function values don't change. It's perfectly level. The derivative would be 0 through that whole interval, say. Okay. So we would name this again with x values. So decreasing would be -1 to 1. Okay, then it would pick up again from 3 to 5. Okay, again, what I'm doing is looking at x values. So that would be 3 to 5 like that. Okay, that would be the idea. All right, now what we're going to do is look at local minimums. A local minimum, you got to find a place on the graph where the function decreases, changes directions, then increases. Okay, how many places do you see that happening on the graph? Okay, one place. What is that place? Yeah, it's this point right here. So this right here, I'll just kind of put a dot there. That is going to be the local minimum. Okay, that's going to occur at the point 1, 2. Okay, next question I'm going to ask is how many maximums do you have? How many places do you see the graph going from increasing, hitting a high point, and then changing to decreasing? Okay, right, there are 2. So you would have there, and you would have there. That would be a max. That would also be a max like that. So that would be the point -1, 4. And the other local max would be at the point 3, 5. Okay, so that's it. Now you may be asking, how about all these other points like these end points? Okay, one thing that's worth writing down is that I would write this down because it's pretty important. An end point is never a local max or a min, And the reason for that is because it doesn't follow the definition. What you have to have is, in order for something to be a min, you have to decrease, then increase. In order for something to be a max, the graph's got to increase, then decrease. So if there's nothing going on on one side because it's an endpoint, then it can't be considered a local max or min. Okay? Okay, next thing is, where is the derivative positive? Okay, that's the same thing as where does the function increase? Okay, so we've already answered that. This graph increases in these yellow regions. So that would be from -7 to -3. And then we're not differentiable there, so then we would go -3 to -1. And then we would go from 1 to 3. Okay, that's the same answer, by the way, as number 1. They're both the same thing. Okay, and then this next one is saying, where is the derivative negative? Okay, a derivative is negative where the function decreases. Okay, so where the function decreases is these blue regions. So that would be from -1 to 1 and from 3 to 5. Okay, so the idea is the answer to number 6 is the same as the answer to number 2. That's it. Okay, the last thing we're looking for is, where is the derivative 0? That would mean, where is the slope of the tangent line 0? Well, it's kind of interesting on this one. The idea with this one is, I only really see one place where this happens. Okay, it happens on an interval. So let me see if I can find, kind of do like another color here. It'd be right here. Well, that's kind of too big and fat. Let's try this. Okay, from here to here, that would be the place where the derivative is equal to 0. All these other places, and see, you're not differentiable at all these sharp points. So if I was to look at all of these points right here, these places there, every one of those, the derivative does not exist. So what we would say on this, kind of a weird way to do this, we'd have to say from 5 to 7. Oh, hold on. I didn't know. That's problem number 7. From problem number 7, it's on an interval. Okay, now this, you might want to make a note of that. That's an interval. Okay, so all of those points from 5 to 7, the tangent lines are going to be 0. They're going to have slopes of 0. Now we're going to find every place where it doesn't exist. So that would be like sharp points. And there's a whole bunch of sharp points on here. One coordinate would be -7, -5. Now that's an end point. So on an end point like that, the derivative is said to not exist. We would have -3, -3. Okay. We would also have -1, 4. That's a sharp point. 1, 2. We would also have 3, 5. And we would have, last but not least, that is, well, I can't tell on here very good. Let's see. I think that's all the way to, yeah, that's to 5, 1. And then finally at that end point. Okay, that end point is 7, 1. So all those places there are going to be places where you have sharp points so that the derivative does not exist there. Okay, so there's a lot of details. What's a little bit different on this problem is you had an interval where the derivative was 0. That was a little different. Then you had a bunch of sharp points, so the derivative doesn't exist at any of those sharp points. And sharp points don't have to look like that necessarily. They could be just a curve and then a line. Okay, that's the graph changes abruptly. That's going to be a place where it's not differentiable. Okay, all right. So I'm going to have you go to the next page and crunch out the next set of problems. Okay, just on this page, and then you can stop there. What I do on this is I'm going to pause this video here a little bit, and and then go ahead and when you're ready to check your answer, just resume the video. All right, so go ahead and pause, answer the questions. Okay, so you can go ahead and check your answers to this problem. There's a couple of little picky details I want to talk about here a little bit. So, and I'm going to zoom on this just a little bit, and then we'll kind of look maybe at these first four here and see if you got these right. First 4 or 5. Let's look at the first 4. Okay, so on this one, increasing, I highlighted those places in yellow. A to B would be 1. And see, you can put this whole interval together. And the thing is, the derivative is not equal to 0 there. Okay, it's not equal to 0, and then that derivative is defined. That's not a vertical tangent line or anything. So you would want to put this interval from D to F. Based on what I see in the graph, if you split it up into 2, that's wrong, because at that point E, the derivative exists and it's not equal to 0. Okay, so that's why you would put that together like that. That's real picky. I probably, an exam and stuff, I might not get that fussy on that, but technically, from what I see, you would put this in one place because the derivative is positive right there. There's a tangent line that's sloping positive. Okay, decreasing, I did the same thing. We did this from here to here. Now, you do have to break this up into 2 intervals because the derivative right there is 0. And in order for a function to decrease, the derivative has to be negative. So from B to C, then from C to D, you have negative derivatives. When you're at C, you would find that f prime of C is equal to 0, so that has to be excluded from the decreasing interval. And then from F to G, you would be decreasing as well. Okay? So again, you can't split. You have to split this up is what I'm saying. You have to, okay? The minimums are the red dots. That would be at D and G. Again, the function changes direction from decreasing to increasing on both points. The local maximums are the points that I highlighted in green. That would be at B, function increases, then decreases. And F, increase, decreases. Okay, not endpoints. Endpoints don't count. And this point right here is not a max or a min, neither is that point. Okay, so that's it. Okay, now I'm going to zoom out on this a little bit, and when we get to number 5, okay, well, the answer to number 5 is the same as it is to number 1. The derivative is positive wherever the function is increasing. So it's the same answer as problem 1. And then the answer to number 6 is the same thing as where the function's decreasing, so it would be the same answer that you would have on number 2. Okay, and let's see, zoom out a little bit more. The places where the derivative is 0, the only places I see are C. Okay, you would have a horizontal tangent line. At D, you would have a horizontal tangent line. And at F, okay? So you're looking for horizontal tangent line on that particular problem, okay? And then the places where the derivative does not exist would be endpoints, sharp points, and any place where the function is discontinuous. This function is continuous everywhere. So you have an endpoint at A, you have a sharp point at B, you have a sharp point at G, and an endpoint at H. That's it. Okay, so those are the answers you should have got on that problem. There's some little picky issues in there with your intervals, but the thing that will kind of help you get past that is increasing. You find places where the derivative is positive. Okay, and if there's a place where the derivative is 0, then that should not be in your interval. A function is decreasing where the derivative is negative. So this should not include places where the derivative is undefined or 0. If you get that definition real clear in your mind, then you'll be okay. And remember that endpoints are never considered a local min or a local max. Okay, so that's it. All right, that's the first thing that you want to try to get established in this section, is how to take a graph and find all of these important properties of that graph that connect to the calculus and the first derivative. Okay, that's it. Okay, now anytime during this video, if you need to stop and get stuff written down or kind of think about what I just said, then do that, then you can resume. That's the benefit of doing videos, okay? You can stop videos, but you can't stop the professor. The professor just goes on and on and on. Okay, so let's see. Let's go to this example. Now, what we're going to begin to look at on this example and the examples that follow are going to be problems where we basically are now going to analyze derivatives, analyze the function, and work these things out. So we're going to look at the function that's given. We're going to make a sign chart. We're going to figure out where it increases and decreases, find the mins and maxes, and then we'll follow it up on the graphing calculator by checking the graph at the end. Okay, so the first thing that we want to do to start with is remember a critical number occurs two places, where the derivative is 0 or the derivative does not exist. So when I ask you for critical numbers, you want to do the derivative. Okay, and the easier the derivative, usually the easier the problem is to do. So that would be 10x minus 10. Okay, now that derivative is always defined. Okay, it's not that expression is not undefined anywhere. That's a line. It's defined everywhere. So what we're going to do is set this equal to 0. So to find the critical number, you set the derivative equal to 0, and then you solve the equation. Okay, so we're going to take 10x minus 10 equals 0. You can solve this equation. You can do this one in your head. It's easy enough to do in your head. You would get 10x equals 10. Divide by 10, so where is the critical number? Okay, it's at x equals 1. Okay, so you only have one critical number in that problem. Okay, so that is always going to be done the same way. Do the derivative, ask where the derivative is undefined, sometimes it will be, or where it's 0. In this case, it was only 0 at one point. That happened at 1. Okay, now we move down here and we make a sign chart. So when we make a sign chart, what you want to do is just draw a number line and locate your critical numbers. In this case, the only critical number is x equals 1. And I like to have students write down that f prime of 1 is equal to 0. So that's where the derivative is 0. Every other place, the derivative is either going to be positive or negative. So what you do is we're going to plug in test points into the first derivative. Okay, the first derivative is 10x minus 10. Okay, so we're going to pick test points and plug into that derivative. Now, what you do is you break this up into two regions, below 1 and above. And you pick any number you want to below 1, and you'll always get the same result. So let's pick 0 and plug that into the derivative. So you would have 10 times 0 minus 10, and that is 0 minus 10, that's negative 10. So it's a negative result. You don't have to get the result of that derivative. You just have to establish it's negative. The reason I put several negatives is because it doesn't matter what the test point is. Notice if I picked, say, negative 5, if I did 10 times negative 5 minus 10, it's still negative. So see, it doesn't matter. Okay, and then I'm going to take a test point bigger than 1. Let's take like a 2 and plug that into the x of the derivative. So we would say 10 times 2, the test point, minus 10. That's 20 minus 10, that's 10. What matters is it's a positive result. Okay, so what you can do, a lot of times you can do the test point in your head, but plug into the derivative. That's real important that you plug your test points into the derivative, not the function. Okay, this tells us a lot actually. Okay, this tells us the derivative is negative. that's going to tell you that the function is going to decrease. And this tells you the derivative is positive. That's going to tell you the function is increasing. So now we can answer questions based on this sign chart. So what we would get is we would be increasing from 1 to infinity, and we would be decreasing from negative infinity until we get to 1. Okay, that answers that question. And what you can do a lot of times on a problem like this is just kind of draw a little graph. Well, this graph's got to do this. It's got to decrease, hit a low point, and then increase. Okay, so it's going to have a minimum, and we're going to find the coordinate of that minimum. So that minimum has to occur at 1 something. Okay, you can tell that's a minimum based on the sketch of the graph I drew. So what we do is we need to evaluate f of 1. Okay, now we go to the function, which is 5x squared minus 10x. Make sure I got that right. Plug in a 1, because what you're doing is finding the y value of that function. Okay, so that would be 5 times 1 minus 10. That would be 5 minus 10, so that's negative 5. Okay, so we got that minimum, we got the coordinate. Okay, we do not have a maximum. You can tell by looking on this problem that you're not going to have a maximum, because a maximum, the graph would have to go like this. It would have a positive derivative, then a negative derivative. That never happens based on that sign chart. So on the next page, just write down that we have none for a local minimum. Okay? All right. So that kind of wraps up everything we wanted to do on that problem. We did the critical point, or the critical number. We did a sign chart, and that determined where the function was increasing and decreasing, which can help you determine whether you have a minimum or a maximum, or sometimes you'll have both. Sometimes you'll have neither. The sign chart tells all. So what I'm going to do now on the graph is just a couple of things. What I want you to do is plot this point, 1, negative 5, and then we're going to take our graphing calculator and just get a relatively accurate graph on this. So let me load up my calculator, and you can go ahead and put the function in your calculator. Okay, and we're going to graph these just to see if everything that we found with calculus looks accurate to us. That's the main idea on that then. Okay, all right. Okay, so I'll get my calculator set up here. All right, and what we're going to put in is y equals, just go ahead, you can clear anything that you have from previous problems, and put in the function, which is 5x to the second, and then minus 10x. Okay, like that. We're going to do a standard window, so I'm just going to go like this. I'm going to put these things kind of at the side here. Standard window, so just go zoom 6, and then here's your graph. Okay, and I'm going to trace at that critical number. So if I trace at 1, that verifies that that minimum is at 1, negative 5. Okay, and that's it. And then what we're going to do is just take maybe the table of values. You can go second graph, get a couple of more good points if you want to. Then we'll have a pretty nice accurate graph. So what I'm seeing on my graph is a 0.00. I'm seeing the 0.1, negative 5, and I'm seeing a 0.20. And then from there you can sketch that graph. Okay? All right, so that's all the information you would get. And if you begin to look at this graph, just see if that graph matches up with everything that we found with the calculus. Okay, is the function increasing from what? Did I do that wrong? I sure did, didn't I? The function is increasing on the interval 1 to infinity. I think this was intended to be decreasing. Yeah, so the function's decreasing from negative infinity to negative 1. The function is increasing from 1 to infinity. And then the only place where the derivative was 0 was at that critical number, x equals 1. So that graph should verify everything that we found using calculus methods. Pretty cool, huh? Heck yeah, it's cool. All right, calculus will tell us everything that we need to know about the graph. Okay, and if you think about as a business student, if you had a revenue function, well, it would be nice to know where the revenue is a maximum. It'd be nice to know where it's increasing and decreasing, when your profit's increasing and decreasing, when it's flat and unchanging and stuff like that. Okay, that's all very practical, important information. Okay, so we'll go to example 4, and we'll do this different example. To start off, to find a critical number, we're going to just do the derivative of the function I gave you. So go ahead and do your derivative. Okay, so you should get that as your derivative. Okay, that's always defined. Remember, you're always kind of looking at where is the derivative undefined. Well, that's defined everywhere. There's no zero denominator, no negative under a radical or any of that mess. Everything's cool. So what we're going to do is we always set that derivative equal to 0 in order to find our critical numbers. Okay, so we have this equation we got to solve. Okay, so the question becomes, how do you solve this equation? Now it's algebra time. Right, you factor. How do you factor something like this? Okay, it's got a common factor. The common factor is 12, but you can also take out the lowest exponent. So your common factor is 12x to the second. So if you're taking out a common factor, work with the biggest. So take a 12x squared out, leave a blank parenthesis. Now fill in the blank. You can do this in your head. What do you multiply 12x squared by to get 12x to the third? You multiply it by x. Check. Okay, make sure that that's right. What do you multiply 12x squared by to get the same thing back? Okay, that's 1. Good. Okay, so that's the factoring. Now what you do is you got two factors. You want to set each factor equal to 0 to determine where those critical numbers are. A lot of times when you get to this point, you can just do this in your head. Okay, what's the answer to this equation in your head? Well, it's 0. If you don't know that, you could divide both sides by 12. You would get x squared is 0. You do square root of both sides, so you would get x equals 0. Okay, this one, same thing. You could add 1 to both sides. You get x equals 1. So the critical numbers are at x equals 0 and x equals 1. Okay, so that would be the answer to the first part of that problem, and that's where you want to start the problem, because you have to do that before you make your sign chart. Okay, any problem with that? Okay. All right. Okay, so let's go down. Let's make a sign chart now. So when you do your sign chart, what you essentially always want to do is you just want to draw a number line. I'm getting all fancy here with that perfectly straight number line there. Okay, so I've got x equals 0, x equals 1. Just kind of divide your sign chart up into these regions. And it's a good idea to write down that f prime of 0 is 0. That's a place where the derivative is 0. And this is another place where the derivative is 0. Okay? And what we're going to do is the derivative, you want to use the factored form. It doesn't matter. I mean, you can use either this form of the derivative or you can use the factored form. I find the factored form easier, and I think you will too. So the derivative is 12x squared times x minus 1. So you're going to plug in your test points. They go in there. Okay, so now it becomes a matter of effectively choosing test points and effectively doing arithmetic. So give me a number less than 0. You read my mind. -1 is exactly what I thought. You're psychic. Okay, so we have 12 times -1 to the second times -1 minus 1. Work out the details. This is 12 times 1 times -2. I look at it like this. I have a positive times a negative. So what is that? It's a negative. Okay, it's -24. You can go ahead and work it out if you want to, but all that matters is that's negative. Okay, that derivative is negative. All right, that's what matters. Give me a test point between 0 and 1. 0.00001, that's a good one. I had in mind 1/2. Okay, so 1/2 is what I'm going to use. And don't freak out if it's a fraction. You don't have to work it out anyway. So everywhere you see an x, put in a 1/2. So we'll have 12 times 1/2 squared times 1/2 minus 1. Okay, what's going to happen, see, is 12 is positive. If you square a positive number, it's positive. 1/2 minus 1 is negative. So you're going to end up with the same thing. You're going to end up with a negative result, okay, on that. All right? Okay, if you needed to use your calculator to work that out, you certainly could, but it's not necessary, really. Okay, test point bigger than 1. What, pi? Okay, yeah, pi would work. I had in mind 2, so let's go with 2. Okay, plug in the 2, so we'll have 12 times 2 to the second times 2 minus 1, so that would be positive times positive times positive. All three of those factors are positive, so that would be a positive result. Okay, so that's the sign chart, all right? So what does it tell you when the derivative is negative? What does that tell you? That tells you the function's decreasing, exactly. Function's decreasing. How about when the derivative is positive? Function's increasing, exactly. That's the purpose of your sign chart then. Right, now we're ready to write the answer on this then, okay? And I'm going to take a little snapshot because we're going to have to go to the next page. So what's important on this is the sign chart's going to basically tell us what we need to know to answer the questions that follow on this. Ain't technology cool? All right, so we are increasing on the interval 1 to infinity. Okay, that's established from your sign chart. Okay, let's go to the next page. Well, paste. Here's my sign chart. The sign chart's going to tell you everything that you need to know to answer this question. So where are you? Hold on. I think I meant for this to be, this next one's probably decreasing. Okay, I didn't change that, I guess, on my handout. Okay, so let's see. Where are we decreasing? Okay, that would be negative infinity to 0 and then 0 to 1. Now, you may ask the question, why don't I just put them all together and go negative infinity to 1? Well, I'll tell you why. Because the derivative, f prime of 0, is 0. It's not positive. Okay, that's why you have to take that out of that interval. So you have to leave that 0 out of that interval, so you write it like that. Okay, so we're increasing from 1 to infinity. That's what the sign chart said. And we're decreasing in those two places. Okay, now if we're going to figure out basically what this graph looks like, what I like to do is just kind of try to figure out in my mind what it's going to look like. This graph is going to decrease, but then it's going to come to a point where the derivative is 0. Then it's going to decrease some more. Then it's going to change directions and increase. So essentially what's going to happen in this problem is there's two places where the derivative is 0. Those places are 0 and 1. So what's going to happen is, look at this. Do you have a minimum? Yeah, you have a local minimum. Okay, that minimum occurs at the point 1 comma something. Do you have a maximum? No, you do not. There's not a place where the function does that, where it increases, then decreases. So that sign chart would have to go from plus to minus, and it never happens. Okay, so there isn't one. All right, now we need to find this y value here, so we need to do f of 1. Let me go to the previous page. That function was 3x to the 4th minus 4x to the 3rd plus 5. Bad short-term memory. Okay, so I do 3 times 1 to the 4th minus 4 times 1 to the 3rd plus 5 and work out the details. So that's 3 times 1 minus 4 times 1 plus 5. That looks like negative 1 plus 5 is 4. So that would close off and give you the answer of the problem. Okay? All right, so the sign chart told us everything we needed to do to answer those 4 questions. Okay? And I guarantee it, when we do the graph, it'll look a lot like this graph I sketched there. Okay? Let's go to the previous page, and let's put this one together with the graphing calculator now. Okay, just see how close we are to being on the right track with this. Okay, so I'm going to go to y equals, and I'll put in the function. Do this along with me now, so kind of sink in your brain a little better. 3x to the fourth minus 4x to the third, and then plus 5. Okay, like this. And again, just do a standard window. So just go zoom 6. And let's see if that graph doesn't look kind of like we did. Let's actually change the window a little bit so it's a little bit more readable. Let's do -4 to 4. And by scale of 1 on x, and on the y's, let's do -5 to 10. Not that. -5. All the way up to 10, and then maybe scale by 1. So let's try this approach, and then graph. Might be a little more readable if we do it this way. Okay. All right, so a couple of things on this. So let's trace at that minimum. That minimum occurred at 1. So if I trace at 1, that'll give me this. Okay, so that's the graph that I get. Okay, and for our graph, let's go ahead and plot that point 1, 4. So we got the point 1, 4 is where the minimum is. Let's use our table. Second graph, open that up. Look at your table, find a couple of nice points if you can find a few. Okay. All right, so let's see. I see 0, 5. I see 1, 4. That's already got. I already got 1, 4. Okay, and then the rest of them are kind of out of range. So the graph, just sketch it. It's going to do something kind of like that. Okay, and that sign chart it says everything. The function decreases, decreases, increases, has one local minimum. Okay, so I'm going to leave these graphs on here just kind of as a record if you need to come back to my OneNote folder at any time and look at this. Okay. All right, so problem done. All right, and the graph should verify that all the results of the calculus were indeed correct. Okay. All right, pause if you need to. Otherwise, I'm going to move on, and we're going to do several examples because there are several things that can go on these problems. Okay, with this one, let's go ahead and do this function. And let's start by doing the critical numbers like we've been doing. Okay, so start with your derivative. Excuse me, gosh, every time I try to cough or sneeze when I'm doing a video, I try to pause it so you don't have to listen to that crap. Sorry about that. Bless me. All right, so here is the derivative. So the derivative is 4x to the third plus 2x plus 1. Okay, now what's going to happen on this is that derivative is always defined. And what's going to happen is sometimes you got to use technology. Because this one also, it's always defined, but also it does not factor. And you don't really, as a student, have any method to factor this out. So what we're going to do on this when we make the sign chart is we're actually just going to graph the derivative. Okay, so draw yourself a number line, and then we're going to graph the derivative. Okay, and see what goes on this. And this derivative, I have a sneaking suspicion that it might, it's hard to tell. It could always be positive. I can see that possibly happen. Or there could be a place where the derivative is 0, but it would require technology to figure it out. Okay, so what we're going to do is we're going to graph the derivative, which is x to the fourth plus x to the second, and then, hold on, that's the function. I want you to graph the derivative, teacher. So that is 4x to the third, and then plus 2x, and then plus 1. And we're going to just do that probably in a standard window. Just do a zoom 6. And let's see what we're getting ourselves into. Okay, so I'm going to slide this over here. And what we're going to have on this is we're going to look at this derivative and kind of see what that sign chart's going to give us on this. So what I see from here on this derivative is, whoops, sometimes I do stuff and I don't know what I even did. Okay, the derivative is going to be 0 there. Okay, f prime of x is 0. Then you're going to have negative values here and positives here. Now don't get confused with what I'm doing. This is giving you the value of the derivative, not the function. Okay, so these y values are all below the x-axis, therefore it's negative. So our sign chart, we're going to have to figure out what that number is. And according to this, you're going to end up having negative derivatives there. And out here, you're going to end up having positive derivatives. Okay, the graph of a derivative will tell you what the sign chart looks like. So that means all we got to do is figure out what this number is. So in order to do that, we have to do this on the graphing calculator. We need to find that 0. Okay, so what you do is you open up the calc menu, you go second, trace, write down the keystrokes if you need to, second, trace, and then option 2 is 0. Okay, then press enter when you do that. Remember, if I get to going too fast, because I get real excited when I'm teaching sometimes, and just pause, okay? Pause the video. All right, so I'm going to press enter, and then I'm going to do a left bound. So I'm going to get to the left of where that x-intercept is, and I'm going to press enter. Then right bound, I'm going to use the right cursor key, get to the right of it, press enter. When it says guess, press enter. Okay, now what it's going to do is it's going to give that point for us where the derivative is 0. Okay, so I'm going to slide this over here then. Okay, so you're getting a left bound and a right bound. So what we ended up getting is that value is approximately point, and that's a negative, isn't it? Yeah, that's, so that point, and I'm going to write this up here then on this derivative. So that point is going to be approximately, come on, I got to move this thing up so I can see what I'm doing. Okay, that point is approximately, dang, teacher. Okay, negative 0.3, let's use like, say 3 decimals, 385, let's say that. Okay, so again, this is the graph of the derivative. Okay, and these are negative derivatives here, negative valued derivatives. Right here, you have positive valued derivatives. Okay, so then the sign chart's done. Okay, we got, this is where the derivative is 0, so it's not a bad idea to write f prime of negative 0.385 is equal to 0. Now we're ready to write everything that we need on this problem then. So where are we increasing? Okay, we'd be increasing where the derivative is positive. Don't get confused because the graph of the derivative is always increasing. This is not the graph of the function, this is the graph of the derivative. Look at your sign chart. So we're increasing from, and we could say just approximately negative 0.385 to infinity. Okay, where are we decreasing? I think this one was intended to be decreasing. Okay, we're going to decrease where the derivative is negative, so that would be from negative infinity to approximately, that's a negative, negative 0.385. Okay, like that. Okay, now, do we have a minimum? Yeah, we would have a minimum right here. Okay, so if I go back to this sign chart that I made with the calculator, what you would end up finding on this is basically if you did this, drew a graph of this, the function is going to decrease, then it's going to increase. So you're going to have a minimum right there. So we would say we have a minimum at approximately negative 0.385 and whatever that y value is. Well, we got that y value we're going to have to get that from the graphing calculator. It's not 0. Okay, we got to evaluate this in the function. Does this function have a max? No. Okay, it doesn't have a max because the graph is not ever going from positive derivatives to negative derivatives. Okay, that's what's got to happen. Okay, so you don't have that. All right, so see, I had to graph the derivative in order to make a sign chart. That's what made that problem different. Okay, now what I'm going to do is we're going to get our graphing calculator and we're going to graph the function. Okay, so I'm going to erase what I have and then let's put in the function, which is x to the 4th plus x to the 2nd plus x. Okay, like this, and then we're going to just graph this. I'll try a standard window. Zoom 6. Let's see what this function looks like. Okay, kind of looks like what we have. You can tell it has a minimum. You can tell it decreases, then it increases. Now, all I'm going to really do on this is I'm just going to trace at this value. So I'm going to trace at negative 0.385, and then that will give you what that y value, that minimum is, and then I can record this like this. So that is about negative 0.215. I'll just round that off like that. Okay, so that's what the graph looks like, and you're not going to really find much on this. Your minimum is like somewhere in here, and then it's good enough if you just kind of wing it. I'm okay if you do that. Okay, so that's roughly what that graph looks like. Okay. All right, and then that would close off that problem, so that would kind of give you everything that you need to know on that problem. Okay. All right, so again, if your derivative does not factor, and if you can't figure out a critical point by algebra, then you have to graph the derivative, and we had to use that 0 function, that 0 command, in order to figure that out. Okay, so that's kind of what made that a little different on that problem. Okay? All right, so that'll kind of give you some of the ideas of how you use a sign chart in calculus to find where a function increases and decreases. That's the idea. Okay? Okay, so what I'm going to go ahead and do is, kind of to wrap this video up, what I'm going to go ahead and do is let's go to the next page, and then we're going to kind of summarize. This is basically going to summarize how the different sign charts can possibly look when you're doing sign charts. So I'm going to just sort of go over these things. What in the world? See how OneNote just does stupid stuff sometimes. I don't think Microsoft understands sometimes how miserable they make a teacher's life. I think screwing up all the time. It has something to do with the way it syncs into the internet wirelessly, I'm pretty sure. Okay, anyway. I'm sure if I call up Bill Gates, he'll give me a refund. Yeah, right. Okay, so anyway, here's kind of what we have. We're going to look at what we call the first derivative test. That's really what we just did, is we looked at the derivative, and we found critical numbers, and then we used a sign chart to determine where we have maximums and minimums, where it increases and decreases. These are all the possibilities. So you want to study these and make sense of them. You don't want to memorize these. You want to build this kind of as they come up. So this would be an example. This is a function. It would decrease, so the derivative would be negative. Then it would increase, so the derivative would be positive. That would be a local minimum. And then the derivative would be 0 there. So the sign chart, our textbook usually just is going to kind of show this. Negative derivative, 0 derivative, positive derivative. This would be the opposite. Positive derivative, 0 derivative, negative derivative. Therefore, that's a max. Okay, this would be an example of the derivative always being positive. The derivative would be positive because you're increasing, then 0, then it would still be positive. So that function would not have a local min or max. A local min or max is always going to happen where the derivative's sign changes from minus to plus or plus to minus. Okay, this one would be another possibility. The derivative would always be negative because the function's decreasing. So it would be negative derivative, 0 derivative, negative. Therefore, you do not have a local max or min. So those are kind of the distinct possibilities when the derivative is 0. Okay, but also sometimes the derivative is not defined. So you don't have a derivative. Okay, you might have a point where you might have a sharp point. Okay, the derivative doesn't exist. So if you did a sign chart on this, the derivative would not exist. That's why we put ND standing for no derivative. Okay, well, what you'd have is a negative derivative because the function decreases. Then you would have no derivative because of the sharp point. Then the function increases, so it would be positive. So in this case, you would have a local minimum. Okay, but you just wouldn't have a derivative, which would mean you'd probably have a sharp point. This is just the opposite situation. You have no derivative. You have a positive, then a negative derivative, so you have a max. This one, what you have on these examples, you have a vertical tangent line. Therefore, the derivative does not exist. Okay, so you have no derivative because that tangent line has a slope that's undefined. So that would have a positive derivative, then a positive. It would just mean that function's always increasing. So there is no min or max. This would mean the function's always decreasing because the derivative's negative. So same thing. Those are really your distinct possibilities that you're going to get into, see. Okay. All right. So what we're going to look at then is we're going to look at this, one other function. So we're going to look at this. This is one where the derivative's a little bit more complex. Okay, so we're going to start on this one by just doing the derivative. And you're going to have to do what rule when you do x, ln x? Right, you're going to have to do a product rule. The product rule is first times derivative of second plus second times derivative of first. So you've got to do that. Okay, so let's carefully do that. The first is x. The derivative of ln x is what? Okay, 1 over x. Plus, now you're going to do it backwards. The second, derivative of first, derivative of x is 1. So that right there is your product rule. First times derivative of second, plus second times derivative of first. And then what's the derivative of minus x? That's minus 1. Okay. What you're going to find on this is the x's are going to divide out. So what you would end up having is that whole thing would be 1. This would be plus ln x minus 1. Well, 1 minus 1 goes to 0, so your derivative is ln of x. Okay, so that's the value of your derivative. That's what we're going to be working with to find critical numbers. Okay, well, all right, so here's kind of what happens on this. The derivative is ln of x. It is undefined somewhere. Let me ask you if you know where that's undefined. What kind of numbers can you take logarithms of? Okay, good. Only positive. Only positive. Okay, so it's undefined whenever x is 0 or negative. Okay, so the derivative does not exist on the interval negative infinity to 0. And actually, I'd have to include that 0. You can't do a logarithm of 0. Okay, so when we do the sign chart, we're only going to think about what goes on for positive numbers. Okay, so I'm going to go ahead and go down and just kind of show you that. So what we're going to end up having in our sign chart is we're going to locate 0. And on that, we're just going to, we don't have a derivative. Okay, now come on, why did it just do that? Is OneNote screwing up again? On. Usually it gives me a message, we're sorry. Okay, instead of apologizing, fix your program. All right, so we got no derivative there, and there's nothing going on there. Okay, the derivative does not exist for negative numbers or for 0. Okay, Now, what we're going to do is the other thing we're going to do is we're going to set the derivative equal to 0 and solve that equation. Okay, so the derivative is ln x. We're going to set that equal to 0. So now you got to dig into your algebra background. You got to know how to solve logarithmic equations. Well, a logarithm, natural logarithm is a base e. You need to write this in exponential form. What is that? That's e to the 0 equals x. Anything to the 0 is 1. So you have a critical point at x equals 1. And that's going to be where the derivative is 0. Okay, so now we're ready to do that. So actually we end up having the only critical number we really have is x equals 1. You need to realize that there's no derivative here. So you don't really have to use 0 as a critical number, but you're only going to look at numbers bigger than 0. So we're going to look at two parts of this. We're going to look between 0 and 1, and we're going to look past 1 when we do our test points, okay? And again, what we're going to do is you're going to plug in the test points into the derivative f prime of x equals ln of x. Okay, and you can use a calculator if you want to on this. I don't care. Okay, so what we can do on this is let's take a test point between 0 and 1. Let's take a half. And let's just plug in. So we're going to do ln of a half. If you don't know how the logarithm of fractions goes, then it's worth knowing. I'm going to do this on the calculator. So if you go ln of 1/2, you're going to get a negative number. Okay, anytime you do a logarithm of a number between 0 and 1, you're going to get a negative number. Okay, so I'm just going to write down that that's all negatives in there. Okay, and then I'm going to do a test point bigger than 1. Let's do 2. So if I did the ln of 2, that will give me a positive value. So what's going to happen is anytime you do an ln of a number bigger than 1, it's positive. Okay, so you can use your calculator to evaluate a test point if you need to, although to me it's actually real helpful to know that stuff so you don't have to dig out your calculator to do that. Okay, so that's what I want to show you on that. So now we're basically on the next page. We'll be ready to answer all the questions we need to answer. So I'm going to take a snapshot of this sign chart that we made, and then we'll go to the next page and then we'll answer all the questions. Okay, so let me just paste this over here. Okay, all right, so now we're ready to rock. So where are we increasing? Okay, we're increasing from 1 to infinity. Okay, the next one is, I think, saying where are we decreasing? So where are we decreasing? Yeah, 0 to 1. Not out here. There's nothing happening out there. That's the undefined there. The function's undefined. So that would be from 0 to 1. Okay, now we just got to figure out, do we have a min or do we have a max? Well, you can just kind of do what I've been showing you. You can just kind of, okay, the function's going to decrease here. Function's going to increase here. So the graph's going to do something kind of like this. Okay, the shape may not look like that roughly, but it's going to decrease then increase. Okay, and then that derivative is going to be 0 there. So that means that we do have a min, but we do not have a maximum in that problem. Okay, so what you would do is you would do this. That local minimum occurs at 1, and then you need to find the y value by looking at the function. So the function was x ln x minus x. Okay, so that's the function we did. So let's plug the 1 in. So we would have f of 1 is 1 times ln 1 minus 1. The ln of 1 is 0. So we would get 0 minus 1, so we would get negative 1. Okay, now the thing about this ln 1, it shows up all the time. That means log base e of 1. The reason it's 0 is because e to the 0 is 1. Okay, so that would be your local minimum. Okay, now we're not going to graph this problem or anything. We've got everything we need to know. Let's go ahead and put this actually in the graphing calculator because I think it'll help you possibly understand a few parts of this graph. So let's graph the function, which was x, ln x, and then minus 1. And let's just do that in a standard window to start with. Okay, zoom 6. So here's kind of what you get on this. Okay, you're going to end up, if I trace at 1, that's going to show you where that minimum is. Okay, and that doesn't look very good. I'm going to zoom in on this a little bit. So what I'm going to do is I'm going to take this from, let's say, negative. I'm going to do something like -2 to 5 and kind of do that like this then. Okay, let's try that. I just want to see if I can see this graph a little. That's more what I want you to see. So let's see. So we had a local min at 1. Now see, I may have made a mistake on this because this doesn't look right to me. It looks like that minimum is not at 1. Let me make sure I got the... Oh, I didn't. Did I? Oh, I didn't put the function in. That's what I didn't do. Okay. So I knew there was something wrong. Okay, so the function is x, ln x, and then I put minus 1. I need to put minus x. Okay, let me try again. Just use the same window. There we go. That's more like it. So if I trace at 1, you can tell visually that's the correct local minimum. Okay, so that's mainly what I wanted you to see on that. Okay. All right, so that will answer, kind of giving us a verification of that graph that we're on the right track. So there's a couple of things I wanted you to notice on this graph. Number one, there's nothing going on out here because the ln of x has to be greater than 0. So this is your min at 1, -1, and you can tell that you're decreasing, and then you can tell you're increasing. So that sign chart does exactly what we'd expect it to do if we looked at it on the graphing calculator. Okay. Okay, that's a problem that's a little bit more difficult for students because it's got logarithms in it. Okay, a couple other things we want to do on this section to kind of get this wrapped up here. So now what I want to look at is, let's look at sketching graphs given conditions. Okay, so what I'm going to have you do on this is we're going to, first of all, we're just going to draw a blank graph out at the side here on this example 7. And we'll do the same thing for example 8. Just kind of draw yourself out a blank graph. Okay, now what we're going to do is we're going to look at each of these statements and kind of put together what a graph would look like if it had these conditions. So I'm going to start over here. A good way to do this is just to write down what I gave you and see if you can figure out what this is going to give you. So this statement right here, all it's going to tell you is that you have a point -2, -1 on the graph. Okay, that's an x value, that's a y value. So what we're going to do is we're going to go ahead and we're just going to plot that point. And then that'll take care of what that statement tells me. That's a point. The second thing I have is f of 0 equals 0. Okay, that tells me that I have a point 0, 0 on the graph. Okay, so I got that. All right, the third thing is f of 2 equals 1. So we've got 2 points so far. And the same thing's going to happen on 3. This is the statement f of 2 equals 1. That just tells you you have a point 2, 1 on your graph. So you want to just plot the point 2, 1 like that. All right, and that gives you what that first line is telling you. It's just giving you points. Okay. Now you get into the next set of conditions. The fourth one is f prime of -2 equals 0. Well, what does that tell you? That tells you that the tangent line is horizontal. So when f prime is -2, I'm going to write a little note to myself that the derivative is 0. I got a tangent line that's horizontal there. Okay. And then the fifth statement says f prime of 2 equals 0. And again, that's going to say the same thing. It's just going to say, again, that we have a horizontal tangent line, meaning that we could potentially have a max or a min, but not necessarily. So far what we got is we got 3 points, and we know 2 places where the derivative is 0. Okay, then we go on to the next couple of statements on this. So the next thing, this is actually all one statement. It's saying the derivative is positive on the interval negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. Now what that's going to tell you is the function is increasing. So from negative infinity until you get to negative 2, that function is going to increase. Then from negative 2 to 2, it's going to increase. And it's going to increase from there on out. So if you think about the graph, it's going to increase everywhere, okay, except where those 2 points where the derivative is 0. So you would end up having something that would kind of have to go like this. You have to go like that. The derivative would have to be 0. Then it would go through there, have to be 0. Your graph would have to do something like that. All right? So that's how I figure out what that graph looks like, is just by methodically telling what each statement tells me about that graph. Okay? All right. So that's it. Now I'm going to let you pause the video and try your best to see what you get on example 8. There's more than one answer. Your graph just has to show that every one of these conditions holds in your graph. But your graph can be different, okay? There's different ways to get a right answer on that. So go ahead and try that yourself and come back and check and see if you got what I'm... Okay, so see if you got kind of what I got. This is what I came up with, is I have a graph that looks like this. What you have to check, and if I was checking this on an exam, this is what I'd do. I would make sure that you have the point -1, -2. I'd make sure you have the point 0, 0, and 1, 2. Okay, you get points for those. Okay, you've got your points okay. Then your graph has to show that the derivative is 0 at -1 and 1. So your graph should show that you have tangent lines that are horizontal. You don't have to write the tangent line on your graph. I just need to be clear that it is. And then there's 2 possibilities on this statement. This statement right here kind of gives you a few possibilities. One way for the derivative to not be defined would be for a sharp point, where you just kind of have a cusp right there, a sharp point. You could also have an asymptote. Okay, if you did this, the derivative wouldn't exist there. Or you could even have something like this. You could have like a bubble like that. Okay, you could have something that kind of looks like that. So I would have to see that there's no derivative at that point, and there could be more than one way that you could do that. And then basically I'd have to see that the function increases from -infinity to -1 and from 0 to 1. Okay, so see if you did it this way, this would also be okay if you did it like that. And then I'd have to show that you're decreasing from -1 to 0 and from 1 to infinity. So that's probably the most obvious way to get that answer, but you could also have a couple other possibilities like that. That's it. Okay, so that's how you put that together. I always recommend to students, don't try to do this all in your head. Write down what each statement tells you about the graph. That'll help you put this together, see? Okay? All right, go on to the next page. All right, so what we're going to do on this is I'm going to put you to work on this one too, and just kind of let you see how much of this you can do yourself. So what you're going to do is you're going to match the graph with its sign chart. Let's just do the first one together so we kind of are all doing this the same way. So, okay, this one, what you would do, this is the way I would recommend you do this. You need to see the derivative is 0 there. The derivative is positive here because the function's increasing. Then the derivative is negative. Okay, let's do that, and let's do 20, and then I'll see if you can do the rest. This one, does the derivative exist here? No. Function decreases, so it would go like that. Function increases, it would go like that. So let's match that up. So let's see which one number 19 is. You'd have to find a plus minus and 0 derivative. Okay, at 3, so see this is at x equals 3, so that one appears to me to be this one. Okay, you have a definite point where the derivative is 0. So that one is E. So just put the letter by the number. The next one, negative, then positive, then no derivative. Okay, negative, then positive, then no derivative. Okay, that looks like this one, so that one is B. Okay, all right, so go ahead and see if you can do the rest. I'll zoom out on this the best I can and just see if you can, from here, figure out the rest. Okay, I'll pause the video and then you can come back and check and see if you got it right. Okay, so check them out and see if you got the right answers. Just match and see if you got it. Study over what I got. I got D on 21, H on 22, F on 23, G on 24, C on 25, and 26 I got A. Now see, what I do is I just write notes to myself. This one has positive derivative everywhere, but no derivative because there's a vertical tangent line. This one has negative derivative everywhere, but zero derivative because you have a horizontal tangent line. Okay, anytime you have a sharp point or a vertical tangent line, the derivative doesn't exist. And then you can look over the rest of those and just see if you get those. Pause the video if you need to think through those. Okay, so that's kind of a summary of what the sign chart is going to do for you then. Okay, all right, I'm going to move to the next page. And we'll finish up with an application here. Okay, so we've done revenue analysis quite a bit. So this graph is giving you a revenue function. The revenue is in dollars. That's the y-axis. And this is the sale of electric screwdrivers. Okay. So what we're going to do on this is this says we're going to write a description of the graph of the marginal revenue, including any discussion of x-intercepts. Okay, so here's what we're going to do is we're going to sketch a possible graph of that derivative. Okay. All right, now, so let's do this. Let's go down, and on this, what I want you to do is just draw a kind of a blank graph here. Now, remember, what we're going to do is we're going to try to sketch the derivative, okay? So this is what I would recommend you do. All right, now, what we're going to do is just kind of use the key points. We have 500 out here, then we have 1,000 out here. Now, the y-axis is going to be r prime of x. So you want to label that. So here's kind of the way I look at this, like this. Right here, the derivative, f prime of 500. What is the value of the derivative at 500? Right, that's 0. So what you do is you put a point there like that. Okay? All right, now the other thing that we get on this is what kind of derivative do we have here? Well, if you look at this, and if you did a sign chart on this, you would have positive derivatives here, and then you would have negative derivatives there. Okay, so that means what this is going to mean is the derivative is going to be below the x-axis, okay, from 500. It's going to be below like that. And then the derivative is going to be above the x-axis there. That's because it has positive y values. Remember, we're graphing the value of the derivative. The other thing is the steepness of this tangent line right here in this region right here. So from 0 to 500, what it's doing is it's getting less steep. Okay? So this is kind of what I usually tell students to do. If the tangent line is at a 45-degree angle, then the derivative has a value of 1. It's kind of hard to tell where that is, or if it ever is in here, but right now the derivative is the most steep. Just kind of think about how your tangent lines go. When you get up in here, the derivative is a little bit smaller. So what you're going to end up having is it's going to end up just kind of being a line like that. Those y values are going to get smaller from 0 to 500. Okay? It's hard to tell if it's at a 45-degree angle there, so if that's 1, is kind of questionable. Okay, then what's happening is the derivative is basically it's getting smaller and smaller because the derivative is getting smaller values. Okay, so what's going to happen is that's going to go like that. So the graph of your derivative actually is just going to be a line that goes like this. Now, one thing that'll help you to understand this is this, to me, kind of looks like a parabola. Okay, it's not negative x squared, but it's a parabola upside down. So the derivative of this would be negative 2x, which would be a line. So that's a parabola. I can tell pretty well by looking at that revenue function, it's a parabola, so its derivative is a line. So that's how I know that. Now, would this be negative 1? It's kind of questionable. Probably not. Okay, it's got to be at a 45-degree angle for that to be that way. So that would be a rough graph of that derivative. That's how that would go. You would have positive valued derivatives here, negative valued derivatives there. That's the graph of the derivative. Okay. Okay. So next thing I'm going to do, that's all we're going to do on that. I think we also want to write a description of the graph of the marginal revenue function. Okay, so what this is going to mean really is we're supposed to do x-intercept. So you would have an x-intercept at the point 500, 0, okay, on your derivative, all right? And the other thing is you would just say there's a couple of things you could say. You could say the derivative or the marginal revenue decreases. Okay, it decreases from 0 to 1,000. So your rate is changing. Okay, so you could write something like that. Okay, next one, average cost. This will kind of wrap us up. So on this next problem, it says a manufacturer incurs the following cost on producing X rain jackets in 1 day on this interval. It has fixed cost of $450. It has a unit production cost of $30 per jacket, and it has equipment and maintenance repairs of 0.08 X dollars like that. Okay, so what we're going to do is we're going to find an average cost function, and we have to build that just based on what they've given us in the problem then, okay? So the first thing we got to do is, after we've read the problem, we got to put together our cost function. Okay, so the cost function, we're just going to use C of X. Okay, well, it's got several things. It's got a fixed cost. So if it's got a fixed cost of $450, that just means that's part of the function. $450 regardless of how many rain jackets we make. Then it has a unit production cost. So every time you make a jacket, it's going to cost $30, so that's 30x. So that 30x is what we would call the variable cost. That's the cost per jacket. Okay? And then the last thing it says is you've got a cost that is dependent on x that we're going to tack on, which is 0.08 x to the second. That's maintenance and repairs. That's going to increase as we produce more and more rain jackets. So that is your cost function. So what we got to do is find the average cost function. The average cost function is C bar of x. How do you do that? You take the function and divide by x. So in a sense, you're averaging that out by dividing by the number of jackets you produce. So that's going to be 450 plus 30x plus 0.08 x to the second. Then we're going to divide that by x. Okay, so in part A on this problem, what we're doing is just finding the cost function. So I would recommend that we go ahead and just split this up because we're going to have to do the derivative in part B anyway. So this would be 450 over x plus 30x over x plus 0.08 x squared over x. So what we'd end up having then is we would have C bar of x equals, and let's write it as 450 x to the negative 1 plus 30 plus 0.08 x. So we had some cancellation of x's on two parts of that problem, see? Okay, so that is our cost function that we're going to work with then, okay? Okay, part B of this problem, now what it says on part B is we're going to find the critical numbers, the intervals where the average cost per jacket is decreasing, where it's increasing, and if you have any local extrema. And then we'll verify all this on the graphing calculator after we're done. So the first thing we're going to do is we're going to do the marginal average cost by doing this derivative. So you want to go ahead and do that derivative. So that's negative 450x to the negative 2. That goes to 0. And then the derivative of 0.08x is 0.08. So that is the derivative of that function. That's the marginal average cost. Okay, you want to go ahead and do these things. You want to set this derivative equal to 0. Okay, so this derivative, let's write this derivative as negative 450 over x squared plus 0.08 and set that equal to 0. Now, there's a couple of things on this. The derivative is undefined at x equals 0 because you have a 0 denominator. So the derivative does not exist at 0. But in this problem, we're only concerned from 0 to 200 anyway. So we're going to find this critical number, and it's probably going to fall between 0 and 200. So we're going to solve this equation. So there's several ways you can do this. What I'm going to do is move this whole quantity to this side. So I'm going to get 0.08 is equal to positive 450 over x squared. Okay, how do you solve this equation now? Get rid of the fraction, so multiply both sides by x squared. Okay, and then what you're going to end up with is, on this side, I'm going to end up with 0.08 x squared equals 450. Okay, like that. And then I can divide both sides by 0.08. Okay, now I need to take my calculator on this when I work this out. So you need to take your calculator and divide out the 450 divided by 0.08. Okay, so let's do that. 450 divided by 0.08 will give 5,000 and something, I think. There we go. Okay, so that is 5,625. Then you're going to do square root of both sides and only take the positive square root. So let's take the square root of 5625, and that gives 75. So that would be a critical number, would be x equals 75. Okay, so we got that. Okay, now what we're going to do is we're going to do a sign chart. So we've got our critical number. So what we need to do is just do a sign chart. I'm going to do this kind of down. Whoops, that's not what I meant to do. Do a sign chart. So just draw a number line. And all we need to worry about is we worry about x equals 0. We're going to go out to 200 because we're only supposed to look at this graph from 0 to 200. And then we'll look at x equals 75 is where that derivative is 0. Okay. Then what we're going to do is we're going to do test points like we've been doing. So we're going to plug in the test points into the derivative. And we'll use our calculator to do this. So the derivative was negative 450 over x squared plus 0.08. Okay, so let's just do this on the calculator. No sense to do it any other way, okay, on this. So let's do some test points. So test point there, what's a good test point? Yeah, I'd say 1. How about here? Yeah, I'd say 76. Okay, it's up to you though. And then plug in, and see, we're just going to do this on the calculator. So we'll have negative 450 divided by 1 to the second plus 0.08. Okay, and that gives a negative number. Okay, so you might want to write on here what we did on the calculator for reference. Okay, so that gave a negative. Now we want to do the 76, so we're going to do negative 450 over 76 to the second plus 0.08, and let's see what that gives. Okay, so I think I got everything in okay. I'm pretty sure it's going to be a positive. And yeah, that gives a positive value. Okay, so that's what the sign chart gives us, and then that will tell us everything we need to know in answering this question then. Okay, so let's answer kind of what we have then. Okay, what would this mean? This would mean that your marginal average cost is increasing. This would mean that it's decreasing. Okay, so what you're supposed to do on this is find the critical number. We got the critical number is 75, so that's an answer to that. And then we're going to write where it's decreasing, where it's increasing, and any local extrema we have. So we would make this conclusion. We would say that we're increasing on the interval 0 to 75. No, increasing from 75 to 200. Okay, and we don't have to go beyond 200 because that's intrinsic in the problem. And then we would be... Did I write this backwards? Did you guys catch what I did? I do this a lot when the video is almost over. I start getting in a hurry. So we're increasing there, and we're decreasing there. Okay, spent the whole time teaching you that, and I get it wrong. So we're going to be decreasing from 0 to 75. Okay, so what does this tell us then? Well, roughly what this is going to tell us is the graph's going to, do something that's going to increase, and it's going to start increasing again. So you're going to have a minimum. So what we would also conclude is we have a minimum average cost at 75 rain jackets. Okay, that would be it. Okay, and that would be the other part of this problem that we could draw our conclusion on. Okay, that's a good problem. So that's a good application that puts all this together. One last thing I want to show you, and you can do this on the calculator if you want to, is, let's see, this is the average cost. The average cost function is this thing right here in yellow. So 450x to the negative 1 plus 30 plus 0.08x. So you want to put that in your calculator. I'll kind of slide these things over here so you can refer to them. For a window, we want to go 0 to 200 because that's what the problem said. Scale by 50 or whatever. 50 is a good thing there. If you look at your table of values, if you kind of scan through this, it looks like the Y values start big and then they start getting smaller. So I think I'm going to do the window kind of like 0 to 400 on the Y's. Okay, so you want to get those two things set up. Then you want to do graph. And then we'll kind of talk about what the meaning of this graph is. You can tell it decreases, hits a low point, and starts increasing very slowly. Well, let's trace that 75. That's where we found that minimum to be. So that minimum is 42. So what you would end up having, you can just kind of make a remark about this, is what you get is this is the minimum average cost, and what it means is 75 jackets produce that, and that cost is $42. Okay, that's how much costs when you make those 75 jackets. So that's where that average cost is at a minimum. Okay, and that verifies everything that we did with calculus methods. Okay, so very good. That should wrap that up. I think I'll play the rest of that song. End of lecture. Have fun with your homework. And thank you.